Hello and welcome back. In an earlier video, I explained more or less how it is that we are able to simulate general equilibrium models in stochastic environments. You could use that video to try and program it yourself. However, nowadays a lot of researchers don't actually do that because there is something out there called Dynare which will do it for you. So today I'm going to explain how you can get hold of Dynare and how you can communicate with it. So Dynare is an add-on to Matlab or to GNU Octave, and it is available for a variety of operating systems. You just go to this website, dynare.org/download, and then you download whichever version of it you want. This thing downloads. I'm going to let it run when it's done. Now you'll notice there are several options here, but notice the last one, Dynare++. That is not checked, but if you don't have access to Matlab, then Dynare++ is a standalone version of Dynare. Click Next. This is going to create a destination folder. Click Install. You'll need to remember that destination folder for later. Alright, now that we have Dynare installed, we can go to Matlab. And before anything else, you have to go to your path and make sure that it includes this directory. I expect that in future versions of Dynare they may change this, so you always have to check the latest documentation. Alright, now that we have Dynare, we have to do something with it. So let's write down first a dynamic stochastic model, and then we'll figure out how to translate it into something that Dynare will understand. So let's go with a standard framework. Suppose agents maximize the expected value of discounted expected utility defined as follows. There's a discount factor beta, and then they maximize log consumption at each period, and minus the following, a constant times their working hours to some power divided by the same power. So what this is doing is it's telling us that these people do not like to work. It's shorthand for saying that they care about leisure. We're going to look at a planner's problem where we're going to assume that there is a constraint on resources. If output is YT, it can be used for consumption or for investment. And in addition, investment adds to the capital stock. The way we're going to write that out is to say that K tomorrow depends on the part of the capital stock that hasn't depreciated yet plus investment. And here what we're going to do is we're going to say that there are investment specific shocks, something that we discussed in other videos. We're going to find it convenient to write it in the following form. Let BT be that shock. Investment specific productivity is e to the power of this shock. And of course, the reason we do that is because the steady state value of this shock is going to be 0, and so e to the 0 is 1. In other words, in the steady state, we're back in the usual environment where the marginal rate of transformation between consumption and capital is 1. Output is given by a production function, which also features shocks. So it's going to be a typical constant returns to scale function, where we've picked a simple Cobb-Douglas function times another shock, which again we're going to find convenient to write out like this, as the exponential of a variable that in steady state is going to be equal to 0. And of course, these constants beta, delta, and alpha all have to be between 0 and 1. Just like B represents an investment-specific shock, A represents a general productivity shock. Now we need to specify the stochastic process for A and B, and the way we're going to do it is as follows. We probably want to allow the two variables to be correlated, and so they follow a joint process where, the way I'm going to write it down, there is a persistence parameter rho that is the same for both of them, and a persistence parameter tau that involves how they influence each other. So this is going to be multiplied by A t minus 1 and B t minus 1. And you can see A has a dependence rho on A yesterday, and the same for B on B yesterday. And then tau tells us how B yesterday affects A and how A yesterday affects B. To this, we will add two stochastic shocks, epsilon t and nu of t, where we're going to assume that the expected value of epsilon sub t times epsilon sub s is sigma sub epsilon squared if t equals s and 0 otherwise. We're going to make the same assumption for nu, except that the value here may be different. Okay, correction. And finally, we're going to allow for some correlation between these shocks. So we're going to say that the covariance of these two shocks is some parameter phi times sigma epsilon sigma v, but again only within the same period. Finally, we need to write down the functions that characterize the dynamic equilibrium of this environment. Now we're going to need to start by writing down the value function. So let's make V a function of the agent's capital and the two shocks that they experience. They're going to maximize their utility in this period plus the expected discounted utility of this value in the following period. Subject to all of the above constraints. This one, the capital accumulation function, and this one, the definition of output. But we can substitute many of these together. For example, this can go here. We've eliminated output, although that doesn't mean that we don't want Dynare to compute it, so we may need to figure out some way to indicate to Dynare that that's an important variable. Then we can rearrange this function so that we have it in terms of investments there, and finally we can substitute it in for investment here. Having done that, we can subtract this from both sides, and we now have an expression for consumption which we can substitute in here, giving us our value function. Now all we need to do is use it to take first order conditions with respect to the remaining variables. Hours worked H and future capital KT plus 1. Now it's time to take the first order conditions. The first one we'll take is with respect to h. And notice that h doesn't show up in the future, so this is just, so to speak, a static decision. Let's derive with respect to h. So we're going to get 1 over this expression. And we have to also multiply it by the derivative of this expression with respect to h. Of course, this disappears, and we end up with this. Then we have to differentiate this with respect to h as well. So this comes down, and we subtract 1 from the exponent, and this whole thing has to equal 0, which is the same thing as saying that these two sides have to equal each other. Now we're going to do some simplification here, because notice that this is just consumption. Also, this of course cancels. And notice also that if I multiply both sides by h, I end up being able to substitute out for this, because this is just output. Now if I multiply both sides by c, we end up with this, which is a very simple expression. You may wonder, why are we doing this? And the answer is because we're going to ask Dynare to simulate outputs, consumption, and so on. And so it's fine if our equations are functions of those things that Dynare is going to compute anyway. Next, we're going to have to take the first order condition with respect to KT plus 1. That's going to be a bit more complicated. So, first of all, the derivative of log is the reciprocal, so we're going to have 1 over this expression. And then we have to figure out what's the derivative of this expression with respect to KT plus 1. There's nothing here. The only place where it shows up is in this fraction. And so, of course, the derivative of this with respect to KT plus 1 is minus 1 over the exponent of b. This doesn't have KT plus 1. And here we just use the first derivative of v. All this has to equal 0. But an equivalent way of writing it is to just take this thing, which has a minus sign in front of it, and move it over here. Notice that this just equals consumption, so we might as well write this. Next, we need to find the envelope condition. So we derive this with respect to its first argument, evaluated at the optimum. Once again, we have natural logs here, so this becomes the reciprocal. And then we have to derive this by kt. So an alpha comes out. This is alpha minus 1 now. Kt shows up here, so we have to multiply that. And there is no kt anywhere else. You can actually simplify this, because notice this is just a ct again. And this expression is output divided by the capital stock. So why don't we just simplify that? So finally, we need the Euler equation. We can just take this and combine it with the above expression. Just need to make sure that we're updating the time subscripts correctly. Now let's start to move a few things around. If you multiply top and bottom of this expression by this, you end up with the following. Of course, this is going to cancel out. which will give us some simplification. In addition, I can multiply both sides by this, and that's going to simplify things even further. Now, if I collect a few terms, like so, I end up with an even simpler condition. There are several ways to write down the Euler equation, but this one works well. Great. So finally, we need to collect all the dynamic equations that characterize this system. First, we have this first order condition. Second, we have this Euler equation. Third, we have the capital accumulation function. And since we're focusing on output and consumption, we could write this as yt minus ct. And finally, we need the individual equations for our shocks. At is equal to rho of at minus 1 plus tau of b t minus 1 plus epsilon t, and one more. We also have that b sub t is rho of bt minus 1 plus tau of a t minus 1. So finally, how do we put this into Dynare? You'll need to open a text editor and then perform the following steps. First, we have the preamble. The preamble is going to be where we tell Dynare in advance which variables it has to worry about in the system. There are two kinds of variables in the system, those that are endogenously determined by the system and those which are exogenous, and the exogenous ones means the disturbances. So first we have to tell it what are the endogenous variables. We write var followed by the list. We have output, consumption, capital, labor, and the two shocks, A and B, semicolon to tell it that you're done. Then the exogenous variables, those are the disturbances, var, xo, and they're called epsilon and nu. We can call them E and U. Next, we have to tell it what are the parameters. And what do we have? We have the discount factor beta. We have alpha from the production function. We have rho, and we have tau. We have delta, we have theta, and we have psi. So that's our list of parameters. Then we have to give them values. So let's say alpha is 0.36, rho is 0.95. These are just values that we're using today. If you were actually programming this in a paper, you would need to come up with justifications for all your values. The psi is 0 value means that utility is linear in labor, which can be interpreted as having indivisible labor. And finally, phi equals 0.1. So there's a little bit of covariance between the two shocks. So we've told it what the variables are, we've told it what the parameters are. Now we have to tell it the model, semicolon. And what we're going to do now is specify these 5 dynamic equations in terms that Dynare will understand. At the end, we're going to write end, so that it knows that we're done with the description of the model. So the first condition is the labor one. So we're going to write C times theta times h to the 1 plus c equals 1 minus alpha times y. So we just literally write it out. The only thing that we haven't done, notice, is mention any time subscripts. And of course, in a sense, we don't need to, because this equation has to hold at every date. The other equations, however, have things that happen at a particular date and at a future date. And it's important to know Dynare's conventions. If the variable is determined in period t, then you just write the variable. If the variable is determined the previous date, such as the capital stock, in this case, you want to write k minus 1 to say that it's yesterday. And if the variable is decided in the following period, such as consumption in the Euler equation, then you need to write, whenever we get there, c plus 1, so we know it's ahead. In this case, everything is determined at this date, so we don't need to worry about it. Next, we confront the Euler equation. So we're going to have that 1 equals that whole expression there. So it's beta times e to the b times c divided by e to the b tomorrow. So we write plus 1 in brackets, times c tomorrow times e to the b tomorrow times alpha times y tomorrow divided by k tomorrow plus 1 minus delta semicolon. Next, we need to write out the capital accumulation function. So k, remember, is determined the previous period. So we're going to write it like this. K is the investment specific shock times investment plus 1 minus delta times k yesterday. Remember, because k is not determined in the current period. We're also going to want the production function for y, since we have it as a separate variable. So that is going to be k that was determined yesterday to the alpha times h, which was determined today, to the 1 minus alpha. Great. Finally, we have the law of motion for our shocks. So A is rho times A yesterday plus tau times B yesterday plus epsilon. And then the equation for B is similar. Just have to switch A for B. And we also have to switch E for U. Great, now we're done with the model. The next thing we need to do is give Matlab some initial values to start with so that it can compute the initial condition from which its simulation is going to go. So that section we're going to call initval. It also is going to have an end. I'm just going to paste in some initial conditions, which are going to be the steady state values for these variables. Notice the steady state value for all the shocks is 0. We're talking about the deterministic steady state. Finally, we write a section called shocks. And what we do there is we're telling Dynare what are the values of the standard deviations. So first, var E is going to tell it what's the variance of E. We're going to tell it that the standard error of this variable is 0.009. We'll do the same for u. And then we need to write down the covariance. So we write var of e comma u is equal to phi times, remember the standard errors of the two things, we end the shocks part and we write stoch simul like that, and we're done. Now you should save this as a file that has mod at the end. I've called it rbc2mod, so you can call it whatever you like. You just need to make sure it's saved somewhere where Matlab can find it. Moving to Matlab, we just write Dynare and then the name of your program, rbc2, and Dynare will run it and produce a bunch of statistics. There's some defaults there about the number of simulations, the length of the impulse responses that it produces, and so on, but you can figure those out by yourself. Here are some statistics that it computes ordinarily. Here is some information about policy and transition functions. These are means, standard deviations, and variances of these variables in the simulation. Probably of most interest is going to be how big their standard deviation is relative to their mean, since that's something you can compare with the data. There's a variance decomposition, so you can see how much of the variance is accounted for by each of these shocks. Here are some contemporaneous correlations among macroeconomic variables in the model, which is another of those statistics that you might want to compare with the data. And here are some autocorrelation statistics so that you can say something about the persistence of the variables. Dynare also makes these figures. These are the impulse responses in the model to the different shocks. One shock is epsilon, the other shock is u. So this is the impact on output, consumption, capital, and so on of a one standard deviation positive shock to epsilon, and here is the same for nu. Alright, that's in a nutshell how you can simulate a business cycle model with Dynare. The example we went through is pretty straightforward, but Dynare can handle much larger, much more complicated systems. Go ahead and give it a try.